Hey, welcome back. In this clip, we're going to focus on differences between gross anatomy and microscopic anatomy in long bones. Remember, long bones are a lot of times what we think of as sort of like a classic bone, like, dog bone kind of thing. But gross anatomy is discussing about what you can see with the unaided eye, and then microscopic anatomy is if we zoom in really closely. So let's begin by looking at gross anatomy. So we just look at a bone on a table. A long bone is going to have a couple of prominent features. One are the epiphyses. Those are the ends of the long bone. So if we look at the ends of this bone, either end you see the sort of protuberances or the big bumps or knobs on the end. Those are called the epiphyses. Okay. And if you look, it's mostly spongy bone on the ends. Along the middle, we have this hollow shaft. It's called the diaphysis. So the diaphysis is where um, blood marrow is stored. Now, surrounding all of this on the outside of the bone is some tissue that we typically don't see when you look at a preserved bone. It's called the periosteum. Peri, think perimeter, and oste is bone. This is a fibrous membrane that surrounds the bone, and passing through this membrane are all these sorts of blood vessels that actually traverse the bone tissue. So bone is this sort of calcified material, but inside of it are living cells. So they're going to need a connection to the blood supply. So wrapped around this bone is this tissue that provides nutrients and allows for gas exchange and things like that. All right, now if we focus more closely on the epiphyses, those ends of the long bones, we'll see the area where long bone lengthening happens. So when a person grows, as he or she gets taller, new bone tissue is added in the epiphyses. Now, note the difference you see here between this x-ray and then the illustration. In the illustration, it looks like solid bone. That's called the epiphyseal line. That is all calcified material. That's like a hardened matrix. That's hard bone. If you look at the x-ray, do you see how it's sort of shadowed there? There's like a black line. So if x-rays can pass directly through material, they're going to land on a film and develop that film, and it appears black. So when you see black in an x-ray, that means the x-rays have passed through, struck the film, and darkened the film. If the x-rays don't pass through, then the film doesn't develop and it looks lighter. So when you look at this x-ray of the bone, the hardened calcified material making up that compact bone on the outside blocks some of those x-rays so the film doesn't develop. Where the dark line where that passes through, that's not hardened bone, that's cartilage. Okay. So the epiphyseal plate, a lot of times people refer to that as the growth plate. So that's a cartilaginous plate where the cartilage gets replaced by bone over time. So if you see an epiphyseal plate, that means there's still cartilage in there, and that person's going to continue to grow. If that cartilage has been replaced by hardened bone, then it forms what's referred to as the epiphyseal line, and that person is done growing. So a doctor can look at x-rays of a person and know if they're still growing or if they're done growing by whether or not an epiphyseal plate or epiphyseal line is revealed in the x-ray. All right. Now, the shaft of the long bone is hollow. It's referred to as a medullary cavity. Now, it may be a hollow shaft, but it's filled with tissue. And this is where different types of bone marrow can be found. Now, in an infant and a toddler, this is referred to as red marrow because that's where red blood cells are being produced. But there's a shift in that tissue as a person grows. That red marrow is replaced by what's called yellow marrow, which is a fatty tissue. And that yellow marrow is a place for us to sort of store fat as an energy storage resource. Now, it's sort of fascinating, but that yellow marrow that's in long bones played a role in human evolution. A long time ago, ancestors of modern humans were able to create hand axes. So they were able to chip away at stones and use those stones as like an axe to crack things open. And what they would find are like basically big bone piles of animals where the ancestors of modern humans could use their stone tools to crack open those long bones and get at that fatty marrow. And the benefit of that is the fat from the marrow could be used to myelinate brains and produce bigger brains. So, because our ancestors were able to crack open long bones of other animals, they were able to access fat that is not in a lot of like vegetation, right? Fat is difficult to come by in nature unless you can get very particular foods. And what our ancestors were able to do was get at some of that fat in long bones. It's sort of interesting because, again, humans aren't particularly fast or strong, but humans are resourceful. So what would happen is other animals would act as predators and kill different animals and consume the meat, and then the carcass would be left behind. Well, human ancestors were probably more scavengers that would take a carcass left by some animal that had eaten it and be able to crack open those bones and get at the fat that other animals weren't able to access. So yellow marrow is something that's important to sort of human history. And you can actually go to restaurants today and they sell bone marrow. What they'll do is they'll like take a long bone, shave it like you see here, make like a longitudinal cut, and then they heat up or cook the marrow and it melts it down and you can add it to your food. So there are places that even sell like bone marrow fries and stuff like that. I've tried it, just sort of buttery. Okay, now there are a lot of markings on bones as well. Bones tell a story, right? So where you see grooves or indentations, those are referred to as depressions, or where you see little projections, those are processes. And one thing that's important to recognize about these bumps or these processes, that is where muscles attach. So if you see there's a bump in bone, then something's probably attaching there. And if it's a bigger bump, a bigger process or projection, well, it's probably a bigger muscle. So you can look at sort of the skeletal remains of an organism and get a sense of where muscles attach and how big those muscles are based on the features of long bones. Okay. So this references a table to look at, which sort of helps identify some of the markings. Okay, now rather than looking at bones sort of on a larger scale, let's zoom in particularly on the compact bone, the stuff on the outside. So if we start with this image here, we see the hardened bone on the outside. What this does is it zooms in a little further. So there's the spongy bone, where the cursor is showing here. And then here's the compact bone. That's the stuff that looks just like the white bone that you're used to seeing in pictures. If we zoom in on that, it shows us sort of the microscopic anatomy. So here you see these rings, okay? So you have these concentric rings where like rings nest inside of rings, which nest inside of rings. We're going to focus in on how that stuff is structured, okay? So first thing we'll notice are the little dark dots. Those are called lacunae. I think of them as like little lagoons, okay? Within the lacunae, that's where bone cells live, okay? So the lacunae are little cavities or little divots in the bone. Again, I think of them as little lagoons. And within the lacunae are the bone cells. And the bone cells are called osteocytes. Osteo meaning bone, cyte meaning cell. So within these little homes, you have bone cells. Now, of course, they are arranged in rings like this. The rings are called lamellae. So I just think a lamella is like a layer. Think of something that's like laminated. It's got several layers. So the lamellae are the layers of rings in this bone. Let's see. Now, taken together, all of this is referred to as an osteon. So if you had a set of rings, that's an osteon. And in the middle, you have what's called the central canal or the Haversian canal. So if we jump back to this picture or this illustration, you could see in the central canal, that's where you have blood supply. So let me move my image here. Here's that periosteum, that fibrous tissue around the outside of bone that has blood vessels. See, the blood vessels travel in horizontally, and then they go in these vertical roads up and down the bone. And then that supplies nutrients to the osteocytes living in these lacunae. So the blood flow comes in, it can travel up and down the osteons, and then that provides nutrients to the cells. One way you can think of it is like a neighborhood, okay? So the whole neighborhood, the whole set of rings is called an osteon. Each street in this circular neighborhood is the lamella. The homes in the osteon are the lacunae, and then the people living in the neighborhood are the osteocytes. Now we're going to add just a couple layers of detail to this. It's the connections between the rings, okay? So we know we have the osteon, we have the neighborhood, and we know that we have the lamellae, so the streets in the neighborhood. How do you get the nutrients from the central canal out to the homes? Well, just like there are alleys that connect streets, there are little channels in the bone that connect the lacunae. Those little channels are called canaliculi, okay? So I think canaliculi, like little canals. So canaliculi are the little canals between the lacunae. They're like little alleyways between streets. And what that does is it provides connection between these cells so nutrients can diffuse. Let's see. So the central canal is in the middle of the neighborhood. What connects it to the outside world is what's called the perforating canal or the Volkmann's canal. The perforating canal is actually a hole in the bone where blood vessels can travel in and hook up to that central canal blood vessel. All right, so that's the microscopic anatomy. Let's talk a little bit about bone formation, and then the last clip we'll talk about all the bad things that can happen. All right, so like in a developing fetus, the first thing that happens is hyaline cartilage gets laid down first. So you get this glossy cartilage put down first, and that acts as sort of like a model for the process of ossification. With ossification, you replace the cartilage with these calcium ions that link together to form a hardened matrix. The cells that do this work are called osteoblasts. And when I remember this, I think anytime I see blast, I'm thinking it's a builder. So osteoblasts are bone builders. So those are cells that come in and deposit that calcium matrix to make the hardened bone. So the thing is, remember, cartilage gets laid down first and it's replaced by bone by these osteoblasts, the builders. Okay, now in terms of how long bones grow, remember that epiphyseal plate we talked about that's cartilage? So in the epiphyses at the end, you have this cartilaginous plate, and then on the outside, you also have a cartilaginous material. What happens is that cartilage gets replaced by hardened bone, and then the long bone lengthens. And then what happens is you keep adding cartilage. So you'll add cartilage here, and then that's replaced by a hardened bone. You add more cartilage, that'll be replaced by hardened bone. So what will happen is you lay down the cartilage first, and you replace it with bone. Then you lay down more cartilage, replace it with bone. Lay down more cartilage, replace it with bone. And in that way, the long bone continues to lengthen. Okay? Okay. Now, not only do long bones lengthen, they also widen. That widening is called appositional growth. Okay? And just like long bone lengthening, it can be under the influence of hormones like growth hormone. So underneath the periosteum, underneath that fibrous layer, you have the osteoblasts adding the bone. So that makes the bone thicker on the outside. On the interior of the shaft, there are other cells called osteoclasts. And the way I think of osteoclasts claw away bone. They dissolve that bone. So osteoblasts add bone to the outside. Osteoclasts remove bone from the inside. And what we notice is that the bone gets wider. If you look, the thickness of the bone in the shaft, it stays about the same. But the distance between the two sides of the shaft get wider. And that's because osteoblasts are adding hardened tissue on the outside, and osteoclasts are removing that tissue on the outside. So the thickness of the walls stays about the same, but the distance between the walls increases. Okay. Now, bone remodeling occurs all the time. You are actually changing your skeleton constantly, because what will happen is your body responds to the demands placed on it. If your skeleton is exposed to greater stresses, physical stresses, it will actually deposit more bone. If your skeleton is exposed to less stress, well, then it removes that bone. So if people are like lifting weights and building muscles, that increased tension will actually cause deposition of greater bone. It's definitely a use it or lose it scenario. So if you are being active and using your muscles, those muscles will pull on your skeleton and it will actually cause your body to deposit more calcified tissue, and it will thicken or make denser your skeleton. Okay. If you're less active and don't use your muscles, that's less stress on your skeleton and you have less deposited bone. One thing that happens with astronauts is when they spend time in space, because their muscles don't have to work that much against gravity, uh, they lose bone density. So, astronauts will spend a couple hours a day exercising, like on the International Space Station, because they're trying to keep their muscle mass as the same as possible, so that they don't lose bone density. All right. We'll come back in the last clip and talk about things that go wrong with the skeleton.